So in question 1 of tutorial 5, we are given a multivariate distribution. So that is, we've got 3 random variables, x1, x2 and x3, and they have a joint density which is given by f. So of course it's a function of x1, x2 and x3. So it's a 3-dimensional joint distribution for those random variables, and we're also given a formula for the conditional mean of the random variable x3, conditioned on the random variable x1 being fixed to be little x1 and x2 to be fixed at little x2. And the formula is as follows. It's a parameter alpha plus a parameter beta1 times the value x1 minus mu1 plus beta2 times x2 minus mu2. And the mu I here just happen to be the means of x1 and x2. And we're asked to find the mean of x3, and we're asked to find the expressions for beta1 and beta2 in terms of the covariance of the random variables. This means that the average value of x3 varies linearly with x1 and x2 in accordance with this formula here. So as the values of x1 and x2 change, we can find the mean value for x3 using this linear equation here. And we'll see a little bit more about linear models in the third question. So this structure here is reminiscent of a formula which you would remember from earlier studies. The expected value of x is equal to the expected value of the expected value of x given y, where we refer to this quantity here as a conditional mean, and it's defined to be a function of the random variable y, where that function is defined as being the expected value of x given that y is equal to y. So to find this random variable here, the expected value of x given y, we need to find this function, and then we need to use it to transform the random variable y. Now in this case things are a little bit more complicated because we're conditioning on 2 random variables, but the formula does extend. So we can say that the expected value of x3, by analogy with this, can be written as the expected value of the expected value of x3 conditional on both x1 and x2. Now this is a little bit more complicated. This is a function. This conditional mean here is a function of x1 and x2. So this expectation is calculated with respect to the joint distribution of x1 and x2. And this expectation here, the inner one, is calculated with respect to the conditional distribution of x3, given that x1 and x2 are fixed. But basically, the formula for this is exactly the same as the formula here. So you see what you need to do is find this function, the one that we're given. Right? So this says for a fixed x1 and the fixed x2, the average value of x3 can be written like this. So we've been told what this random variable is here. I can write it down straight away. I can write this as the expected value of. Now this random variable just replaces little x1 by big X1 and little x2 by big X2 in this formula here. So this conditional mean can be just written as alpha plus beta1, the random variable x1, minus mu1 plus beta2 times x2 minus mu2. And when you take expectations through here, you can see this is just mu1 minus mu1. So this term drops out and this term drops out. By definition of the mu(i), they're equal to the mean of x1 and x2. And so that answers part A of the problem straight away. That's just alpha. Now, in the second part of the question, we need to find expressions for beta1 and beta2. And to do that, we were asked to define sigma ij to be the covariance of xi with xj here. So let's just consider one of those covariances we'll calculate. Let's consider sigma 1, 3. It's defined in the question to be the covariance of x1 or x1 with x3. Okay. Now you can see when I look at the average value for x3, I have an x1 minus mu1 term here. And if I was to multiply this by x1 minus mu1, I'd have x1 minus mu1 squared. And so that's of the form of the variance. And so I'm looking ahead here. I'm trying to explain why. I'm tempted to rewrite this so that instead of having x1, I have x1 minus mu1 because the algebra will work out a little bit better. So I'm going to write this as the covariance of x1 minus mu1 with x3. Now, why can I do that? Well, intuitively, the covariance of two random variables is a measure of the linear association between them, the degree to which their relationship can be described as linear and either positive or negative. So if I replace the random variable x1 by x1 minus mu1, all I've done is shifted the bivariate scatter plot by a distance of mu1, and that will not change the relative shape of the variables at all. So that's my intuitive argument this is the case. Now you should be able to prove it's quite straightforward, but if you consider the covariance with x minus a, where a is any constant with y, you should be able to show that that's equal to the covariance of x with y. And I can shift by any constant there. It doesn't necessarily have to be the mean of x, but I have used the mean of x here. So prove that just using the basic definition of the covariance. It's pretty straightforward. So the covariance, another way of thinking about the covariance is that the covariance of two random variables is the difference between the expected value of the product, x times y, the expected value of the product, minus the product of the expectations. Using this rule for the covariance, you can see straight away that if random variables are independent, this expectation here factorizes and it's equal to that. And so the covariance is immediately equal to 0 if the random variables are independent, but the reverse is not true. So but using that, I can write this as the expected value of the product of these two. So that's x1 minus mu1 times x3. And then I have to take away the product of the expectations. That's the expected value of x3, which I know is alpha, but it's multiplied by the expected value of x1 minus mu1. Because I've taken the mu1 off, this term goes to 0. So the only thing I need to calculate is this, the expected value of x1 minus mu1 times x3. Now, how are you going to do that? In this context, the problem is inviting you to think, well, I will use the conditional mean. So that's a sort of step that you have to think of using. So what I'm going to do is I'm going to say this is equal to, and I'm just going to condition here on x1 and x2. So I'm going to write this as the expected value of the expected value of x1 minus mu1 times x3 conditional on x1 and x2. That's really just using this rule in this sort of context where you're conditioning on two random variables. Now there's one more important step I need to put in before I process this. Think about what these expectations are with respect to this internal random variable here, this conditional mean, it's conditioned on two random variables. So it'll be a function of x1 and x2. And so this expectation is with respect to the joint distribution of x1 and x2. But inside here, this expectation uses the conditional distribution of x3 given x1 and x2. So in other words, it'll involve some sort of integral. You have to multiply by a conditional density of x3, given that x1 and x2 are fixed. And because x1 is fixed, this term here can come outside of the expectation. x1 is fixed. This is a constant with respect to this integration, so it can come out. So I can write this, and it's quite an important step to be able to understand. You can write this as the expected value of, you can write it as x1 minus mu1 times the expected value of, and we're just left with the x3 inside, given both x1 and x2. This I know because it's just sitting here. I wrote it down before. I get it by making x1 and x2 into random variables in this definition here. Okay, so this is the expected value of x3 given x1 and x2. So I can write that in. It's the expected value of, now I've got x1 minus mu1, and then here I've got alpha plus beta 1 x1 minus mu1 plus beta 2 x2 minus mu2. So of course I have to multiply that out. Now this is a constant. The expected value of x1 minus its mean is 0, so this first term here goes to 0. Now, as I said, the whole reason for shifting this by nu1 is so that I get this nice expression here. I've got x1 minus mu1 times x1 minus mu1. So I've got beta 1 times the expected value of x1 minus mu1 squared, which by definition is the variance of x1. And here I've got beta 2 times the expected value of x1 minus mu1 times x2 minus mu2. And that by definition, that is the covariance of x1 and x2. So I can write this as beta 1 times, now I haven't actually said this, but we're given in the problem that the variances of each of the xi are a sigma I squared. Okay, so the variance of each xi is sigma I squared. So we've got beta 1 sigma 1 squared plus beta 2 times the covariance of x1 with x2. And that's an expression for the covariance of x1 with x3. Okay. Now to get the equations that you need to get, you need to repeat the argument and get an expression for the covariance of x2 with x3. Okay. Now you could do that by just repeating this whole argument with a 1 here instead of a 2, but there's a symmetry in this. If you look at this, if you interchange 1 and 2 in this expression, it doesn't change. Change a beta 1 to a beta 2, x2 to x2, nu1 to nu2. So when you repeat this argument, all you're going to do is wherever you see a 1, you're going to replace it by a 2, and wherever you see a 2, you're going to replace it by a 1. You can work through the whole thing just to satisfy yourself that that works, but we can immediately write this down. We've got beta 1 there, so it becomes beta 2. We've got sigma 1 squared, so it becomes sigma 2 squared. beta 2 becomes beta 1, and sigma 1, 2 becomes sigma 2, 1. But sigma 2, 1 is just the covariance of x1 with x2. And the covariance of x with y is equal to the covariance of y with x. So this order doesn't make any difference. So I can simply write this down still as sigma 1, 2 because it's equal to sigma 2, 1. And that's essentially the solution to the problem. The exact equations that you need to get come from some fairly significant algebra on these two. But the key to solving this question, to understanding this question, is to understand that you need to use conditional means, how they are defined, so that this equation here tells you this function, and when you replace x1 and x2 by the random variables, you actually get the, by definition, you get this conditional mean here. So that's really important. And the other important step here was to realise that because we're conditioning on x1 and x2 here, x1 is fixed, so that this term can come outside of the inner expectation, and that enabled us to evaluate that. And that's really the guts of question 1. So have a look at question 2 and then come back to the second video in this sequence.